by this times this minus this times this. So it's AY, AZ. Let's write it underneath it. Minus BY, AZ. And then it's, so that's I, then minus J. And then we AX, BZ. AX, BZ minus BX. AZ. And then plus, that's I, J, and then K. And then it's this times this minus this. This is AX, BY, minus BX. This is C, is A, the two vectors, A cross B, cross product between two vectors. It's the determinant of that matrix. Let's say we have R is 10I plus 10K. I and K being the unit vector, so it becomes this is, let's say, your A vector. And we have B vector is F. This is the force. So here we're taking a force and multiplying it by a distance or a radius, let's say, R. And this is, let's say, 20I plus, sorry, minus 20K. This is in feet units. And this is in kip units. So we're going to take the cross product to get the applied torsion. So we have a force, but the force is offset from a point that we want to take the moment about. And so, and it's not a perpendicular distance, so we'll use the cross product for that. I direction Y, so it's J, and Z. In terms of the force, you can see they're acting in the X and Z direction, nothing in the Y. The force is 20, so out here, let's say, and then minus 20 in that. This is 20 and minus 20. That's the force. And then the radius, or the R value, is 10 and 10. So here, like that. This is 10 and positive 10 with that. And so what it is we're going to say that and this is the O point. M sub O is equal to R cross F. So that's a cross product. It'll be perpendicular to the plane that it makes sense. These are both in this plane and the Z X plane, and then M sub O is going to be like this, perpendicular to that plane. This is M sub O. Okay? so it's like, I mean, the force is shown here, but it's actually being applied out at this location. That's the distance from here to here. So it's like this, right? And so you can see when you place it here, this is how the vector is defined, but when you place it out here, this force multiplied by this distance r, that's going to be a moment about O, right? Because the force is offset. So that's what the m sub O is saying.
Never uploads anymore. His last video was like, I'm coming back, you know. How Scott Bell. Differential equations? Yeah, I'm gonna finish it. He never came back. He's a family man now. He left us broke. He left us heavy. He left us heavy. Full three components, one of them 0 for both vectors. That's right. And then we have here, AY is 0. So this goes out. Yeah.
Should be the I minus J.
Where?
For C equals all that
No.
I minus all
Plus. These are switched. If you look over here, this is minus J, right?
Yeah.
but then I switch these two. So this becomes positive. Same thing as putting the minus. Right? This is minus j this is minus j that, same. And then this minus times minus, that's plus, it's the same as that plus. Okay, so we have that's a 0. Let's see. What else is 0? dy is 0. So this goes out to 0. And anywhere else where there's a, and then this is ay is 0, this goes out to 0 also. Oh, and this is a dy, and this is 0 too. So both of those terms go out, and both of these terms go out. So we end up with C is only the j component. Times bx, which is 20, minus ax, which is 10, and bc, which is minus 20. So this is 200, that shows 400. And then that's equal to m sub o. 400 cubic. And it's there's a j here still, right? So this is times j. So m sub o is 400 plus j, and j is in this direction. So now we know this value is 400, and it's a positive, which means it's going in this direction, which makes sense. You apply the force this way, this times this. It's going about like that. And so if you put your thumb in that direction, the direction your fingers are curling, the direction of your thumb is the positive direction. Look at a moment of a force about a point. Let's say we have this circular section here. And let's say here we have let's go like this. Let's say at this point, I have a force at some angle like that, F. This is the R, like that. And if I extend this line like this is the D. This is 90 degrees. R is the perpendicular distance between the applied force and, so the center of action of the force, if you follow that line, multiplied by V would be that moment about O. So we have moment O is equal to R cross F. Exactly. So it doesn't have to be, it's also equal to, also, the moment O is just F multiplied by D. Right? It's the force multiplied by the perpendicular distance. But in terms of this cross product, you don't need to have that perpendicular distance. It automatically corrects for that. So you just have a force multiplied by the distance between the point you want the moment and the application point of the force. That's the difference. That's where the cross product is. And the magnitude of M sub O is R F multiplied by the sine of theta, which also equals FD. And this is just a scalar, not a vector. Those are the magnitudes. Magnitude of M sub O.
What would be theta?
It's the distance, the angle between the two vectors. It's the angle between the two vectors. All the two vectors in this case, one's a distance, a length, a position, and the other one's a force. But they're both vectors, so there can be an angle between them. And you have, so instead of A and B, this is R and F. So it's the angle between R and F. R is a vector, and F is a vector. F's a force, R is a distance, but not just a distance, it has a direction, right? You can see this has a direction. So it's not just the length. It includes that. So R equals, let's say, 10 I. Oh, we'll come back to this. 0J, so that goes out, plus 10K. So it's 10I plus 10K. And F equals 20I plus 0J minus 20K. So just let's look at, let's say we just have a blob, and here's our O point, like that, and I have a force like this, and distance here, and in this case, this is 90 degrees, right? So it's creating a moment about my O point, this being O. So if that force was right here, there's no moment, right? Force times 0. It's the fact that you're applying a force here is wanting to turn it counterclockwise. That's the moment. And that's what this cross product is doing. So in this case, we just have M sub O is F times D. That's it. You get something like that. Now let's look. We've got this, and again, an O point here. I've got a force like this, now you can see, again, if this force moves over here, if it's applied right down the center, it's going to pull on it, but it's not going to create anything in turning action, right? And now the moment is this way, and again, M is F times M sub O. In this case, it's clockwise. That case, it was counterclockwise, because of the direction of the forces. Let's say you have a case like this. And this is a certain length here. These are just distances. I have a force applied vertically here of 200 pounds. This is length 5 feet. This is 50 degrees. Yeah. Oh, I said 50, but and this is our D distance here, which is, let's write it. This is the point O I want to calculate the moment about. So you can see it's going to be this way, clockwise, M sub O. And we know this is 5, so we have 5 multiplied by the cosine, 50 degrees, is 3.21 feet. So this D distance is 3.2. So again, the moment, you can see it's clockwise about this point. It's just this force. Even though it's applied up here, you extend that, right? And it's this perpendicular distance that you want. And we knew this is 5 feet, so that horizontal distance there is 3.21. So we have M sub O again is FD, which is 200 times 3.21, or M sub O is 642 pound-feet. And you can see it's clockwise. Now, if it was sticking out here, so it doesn't have to do with the fact that force is down, okay, as far as clockwise. Clockwise is clockwise. So I could just as easily have a member out here apply the force up, and if it's off to the left, it would still be clockwise. It would still be in the same direction. So don't get confused with, okay, down means clockwise, up means counter. That's not true. Depends on the position of everything. Depends on where you're taking the moment, depends on where the load's applied. Okay? Here again, same structure there. Here's my O point. This is 5 feet up, and at the top we have a force, a horizontal force of 150. 150 pounds. Okay, and this is 50 degrees again. And we want to be able to determine, you can see it's going to be a clockwise moment like that. We just need the vertical distance. So we need this distance, right? That's our D. Because it's the force times the perpendicular distance. So I don't want to multiply that by 5, I want to multiply it by this if I'm just doing the force times the distance. If I'm doing a cross product, then I could just take this directly, but then it's a whole vector cross product as opposed to just 2 numbers. So I have M sub O is, well, let's see what the D is. So it's 5, multiply the cosine gives me this, the sine gives me that. Sine of 50 degrees. It's a little little different. This was 3.21, this is 3.83. That's 575 pound-feet. Okay, looking at this again. Here's my structure. Now I have the force in this direction, 50 pounds. And this distance again is from here to here is 5 feet. And this moment, about O is m sub O. In this case, the force is aligned, right? So that I don't need to take the components of it. I can just use the force multiplied by 5. So I have m sub O is F times E. And this is E in this case, because this is 90 degrees. So I have 50 multiplied by 5. So that's 250 pound-feet in the clockwise direction. Yeah.
Why didn't you like extend the D distance on that example specifically?
Because this is already this is.
The force is already at like a 90 degree.
That's what that little square I added was, yeah.
And if it's not, then there's gonna be a D distance. either
Yeah,
on the Y or the
I mean,
X.
last time, it's always, the D distance is the perpendicular distance from the force to the location you take in the moment. So this is already perpendicular to that. So if it was like vertical, I did horizontal, same thing. And 75 pounds partway along, this is 2.5 feet. And this is M sub O. In this case, again, this is 90 degrees, the way this load is applied. So it's just, this is my, in this case, this is my distance. It's not the whole length of the member, it's the shorter distance, it's the distance offset. Where the force is applied, this is O here. So I have M sub O is 75 times 2.5. That's 188 pound-feet. Look at another example. Again, 50 degrees. It can be any angle, and this is just examples to see different possibilities. So again, I go up this distance, 2.5 feet. And now the force is applied like gravity in the vertical direction. Down 60 pounds. So in this case, the D distance, right, will be this. Horizontal distance. Since the load's applied vertically, I need this. And so I'm gonna have to take 2.5 times the cosine of theta. D is 2.5 times the cosine of 50 degrees. That's 1.61. And then M sub O, this being O, here's M sub O. Is F times D, which is 60 multiplied by that perpendicular distance. 60 times 1.61. So that's 96.6 pound-feet. point O. This is some kind of structure here. That. And at this point, I have this is 10 feet. And 5 feet up along the center lines. And I have a force applied at A up here. That's at an angle, so 600, not 600 pounds, 600 kips, so it's 600,000 pounds. It's like this, and 30 degrees. 600 kips. And we have, so this is F, this is your vector F, and then we have from this point here to here, that vector is RAO. R is A, and they are not 90 degrees to each other, so we're not just going to multiply 600 by that. There's some angle between them. So in this case, we'll use the cross product, and we're going to use these two vectors, okay? This is the A and the B vectors, which is R sub O. So you multiply, you do a cross product, and that'll give us this, the moment about that location, okay? So we have, F is, the magnitude is 600 kips. We have F in the X direction, so this being X and this being Y, is, I didn't give you the, this is 30 degrees up. So 600 times the cosine of 30 degrees, that's 520 kips. That's the horizontal component. F of Y is 600 times the sine of theta. So that's 300 kips. So F is 520 times I. That's that unit vector, plus 300 times j. Here's our structure again, without, more like a free body diagram. There's F, and then this is F of X, and F of Y. Which is 520I and 300J. And then this is M sub O. 5 feet and 10. So we have F is 520I plus 300J. RAO is minus 10I plus 5J. So that's the position here. 520, 300, 520I, 300J, that gives us this F. And then as far as the direction goes, we have minus 10I, this is your I direction, J direction. So we go minus from here, minus 10. And up 5, so that's this. That's the R sub AO. Minus 10. Plus 5. Okay, so we have M sub O is R sub AO cross F. So we're just gonna do the cross product directly and see what comes out. So this equals, minus 10I plus 5J cross product. So that's one vector. Let's write it more clearly. 520I plus 300J. So if all comes out right, we should be able to go through all the math of this, and what ends up is the actual moment about, this, from the cross product directly, these two different vectors. Rather than just taking a force and multiplying by distance, we're doing it this way. And we end up with, this is equal to minus 5,200. I cross I minus 3,000. Let's put brackets around these things. I cross J plus 2,600. J cross I plus 1,500. J cross J. Okay, let's look at this for a second. So you have, let's start here. It's minus 10I cross that. So that's the minus 5,200. I cross I. And then minus 10I cross 300. So that's the minus 10. Those are constants, the 10 and the 300. So that's minus 3,000. I cross J. Right? So now I go to this one. So I'm just doing the sort of multiplication out from the different terms. Now I go to this one. It has to be crossed by this and this. So it's plus 5 times 520. That's the 2,600. J cross I. And then plus 5J cross 300J. So that's the 1,500 J cross J. And what we know is the advantage of this is now I cross I, remember, is 0. So this is 0. So this whole term disappears. J cross J is 0 also. Now I cross J, what is that? Remember? It's K, right? This is K. Remember, these are all unit vectors. They don't have any value other than 1. They're 1. But if you go back and look at your notes, we were looking at it. Remember, because I, J, and K form a triad, and the cross product between two vectors gives you a vector in the 90-degree direction to the two vectors that make up that plane. So if you got I and J plane, whatever it is, the cross product will be 90. So K is 90 to that, and the value is always 1, right? It's like 1 times 1 is 1. So this is K. Now remember also that when we reverse I and J, when it's J cross I, instead of A cross B, it was B cross A, it was minus. It's a negative K. Just meaning that instead of pointing up, the K is pointing down, let's say. Or instead of one way, it's pointing the opposite way. So this, we know from our work before, this is minus K. That's a big deal because now, first of all, we can eliminate all of this. And now this is just minus 3,000 K. And then this is just plus 2,600 times minus K, which is just minus 2,600 K. We can add these two together now because they're both K. Whereas before we couldn't. We had a mess. So we've simplified it significantly. What we end up with is M sub O is minus 5,600 times K. And K just gives us the direction. If we look at it, the K, it has to do with this coming out of the board. Let's see. Just say, therefore, M sub O is 5,600 kip feet in this direction. Like that. And the way you know it's that direction is, let's draw this point here. There's X, which is our I. And we have our Y and our Z. This. Y is our J. Yeah, this is Y, which is our J. And our Z, which is K. This value is minus 5,600 K. This defines my positive direction K, and so if I got a positive here, if it was positive 5,600 K, it means it points in this direction, right? But it doesn't, it's negative, so it's like this. So it's 5,600 like that. And so if you point your thumb in the direction of the moment like that, and you curl your fingers, it's consistent with M sub O. So that's what the negative means when we get a negative like that. It tells us it's this direction. So I drop the negative and I just show it the direction. If we had a positive, it would have just meant the moment was going this way. And notice how the force vector and the position or displacement, this radius vector, were both in the X and Y, the I and J planes, right? But what came out, all the IJ terms canceled, and we ended up with the K result. And that's because the result is exactly 90 degrees to the plane. That's why it was canceled. And so we were either going to get a result this way or this. Well, the cross product gives us a result that's perpendicular to the two vectors that make it up. Cross product. Okay, I'll take a short break. I'll be back. replace this force with the two components that make up the force, 520 here and 300. I'm taking moments about O. And so this also adds up to 5,600. Same that we got from the cross product. So and they're both clockwise. About both. 520 from 5, that's a clockwise one, about an axis coming out of the page. And this 300 times 10 is all. Same result in the same direction. So we have a cross product and we have the scalar product. Scalar product is A dot B. These are vectors. A dot B is equal in magnitude as AB multiplied by the sine, cosine of B. These are the magnitudes. And so you've got some vector here, another vector here. There's an angle between them. This is B, and vectors B and A have magnitudes. So a scalar product, A dot B, gives you like A times B. It just gives you a scalar. It's not a vector. And this is called the scalar product or dot product. And A dot B is a scalar. It's a single number, not a vector. Vector A is AXI plus AY J plus AZ K. Those are the three components, and in the X, Y, and Z directions, the I, J, and K are vectors. So A is a vector, but the individual values AX, AY, and AZ are not vectors. We have BXI plus BYJ plus BZK. A dot B is plus AZK dot and the B vector. A dot B equals B dot A. Called the commutative law. And A dot B plus C equals A dot B plus A dot C. Distributed law. A dot B plus A dot C. So we have I dot I equals 1. So this is different than I cross I. I cross I is 0, right? Because I cross I would give you a vector. I dot I is the value. Each one has a value of 1, so 1 times 1. We have, remember, A dot B equals AB cosine of theta. So in this case, I and I are aligned with each other. So here we have theta is 0 degrees. So cosine of theta is, let's just say cosine of 0 is 1. And A and B values are 1. So A dot B in that case is 1 times 1. 1 times 1, that's the A times B, and then cosine of theta is 1. So that's how we get I times J, I dot J is 0. I dot I is 1. I dot J is 0 because I and J are 90 degrees. And so we have, in this case, we have cosine of theta. So cosine of 90 degrees is 0. And so we have A dot B is AB cosine theta. So we have 1 times 1 times 0. That's right. See that? AB cosine theta. Cosine theta is 0. Because theta is 90 degrees. Let's see what else. So following the same logic. I dot I is 0. J, sorry, 1. J dot J is 1, and K dot K is 1. I dot J is 0. J dot K is 0, and K dot I. So we have A dot B. Now we're looking at multiplying all these terms together. So we have AX, BX, I dot I, plus AX, BY, I dot J, plus cross dot. Plus AY BX J dot I plus AY BY J dot J plus AY BZ J dot K plus AZ BX K dot I plus AZBY K dot J plus AZBZ K dot K. Okay, let's just take a quick look here. So I'm just multiplying. This one has to be multiplied or dotted with this, and plus this one dotted with this, plus this one dot this. So that's where the 9 terms come from. So the first row up there is this one dotted with this. So let's just check. AX, BX, II, that's I dot I, that's correct. AX, BY, I dot K, that's correct, the second one. And then AX, BZ, I dot K. And the next three, so the second row up there, IY, J dot I, AY, BX, J dot I, that's correct. AY, BY, J dot J, AY, J dot, AYBZ, J dot K, that's correct. So this first two rows are correct. The third one is this, multiply by each of those. So dot product. AZBX, K dot I, AZBY, K dot J, plus AZBZ, K dot. All right, so those all look correct. And now, you have to be careful because it's not the dot that cross product, it's the dot product. So this here, I dot I, this is 1. Right? I dot J is 0. J dot K is 0. So we can eliminate a lot of this. J dot I is 0, look at that. J dot J, this is 1. All right, J dot J is 1. J dot K, this is 0. K dot I is 0. K dot J is 0. And K dot K, this is 1. So it turns out A dot B is just this. AX EX plus AY BY plus AZ BZ. And it's like I said, it's just a scalar, right? It's just a numerical value. It doesn't have a direction. So the nice thing is you don't have to go through all that. You just take the components in the x direction for the two vectors and multiply them by each other. The components in the y and the components in the z, and that's the dot product between each other. Okay. And A dot A equals A, because AX and BX would be the same, so this is AX squared plus BX squared plus CX. Sorry, I wrote this wrong. This is AX squared plus AY squared plus AZ squared. Yeah, these are just scalar values, single values. Scalar values. No direction. Now angles between vectors. includes three-dimensional, like if you have different vectors in different three-dimensional spaces, different directions, you can get the angle between them regardless, which would be hard without this. So your vector A is AXI, BX, sorry, switching, so plus AYJ, plus AZK. And your vector B is BXI, BYJ, plus BZK. Again, those are coefficients. What makes these two things vectors are the I, J, and K vectors. Without that, they wouldn't be vectors. And then AX, AY, AZ, as well as BX, BY, BZ, those are scalars on those little vectors, those little A dot B is AB cosine theta. And A dot B is AX BX plus AY ZY plus AZ. So therefore, these two dot product right? So AB cosine theta, theta being the angle between the two vectors, is just AX dx plus AY by plus AZ CZ. And this gives us the way we calculate the angle between the vectors. Hold on a second. So you get cosine of theta. You just divide this, so you have AX BX plus AY, BY plus AZ, CZ divided by AB. That's the angle. AB is just two magnitudes. This is the magnitude of A. It's multiplied by magnitude B. These aren't vectors, right? These are just the components of the two vectors, but they would be I, J, and K. Right? Some of that question.
Where does the CZ come from?
The CZ. I don't know. It's not supposed to be there. It's from my head. From an unknown phone. Okay. Let's take this. This is E, Z, I don't know CZ. Is the rest right? Okay, so let's look at an example. Two vectors, for you a three-dimensional one. So we have, here's X, I, J, and K directions. And we have two vectors. There's A, which is 10I plus 0J plus 6K. And B is 7I plus 0J plus 2K. So this goes out and it's in the I and K direction, so both of them are going to be in this plane. Okay? So we have A is 10 and 6. This is A vector. And the B vector is like this, shorter than A. And so here, this was 10. And then this direction was 6. B direction. This one is 7. And 2. Right? So that forms the A and B. They're both in the XZ plane. So the magnitude of A is 10 squared. Well, let's rewrite the vector so we can eliminate the 1 term. So 10I plus 6K. And B is 7I plus 2K. So the magnitude of A is 10 squared plus 6 squared square root. It's 11.7. It's just a hypotenuse. And the magnitude of B is 7 squared plus 2 squared square root. That's 7.2. The magnitude of vector A. This is the magnitude of vector. So we have AX is 10, BX is 7, AZ is 6, BC is 2. So the angle between these two vectors, and so when we say the angle between the vectors, we're talking about here's A, right? That's theta. In this case, it's in the plane. So if you drew it looking down like this, this is X, this is Z. This is Y. You would have this is A, B, this is that angle, right? That's looking down. And we know now the cosine of theta is 10 times 7 plus 6 times 2 divided by the two magnitudes multiplied by each other. They do 11.7 multiplied by 7.2. So the cosine of theta, the angle between the two vectors, is 0.960. So theta is the arcsine of that. Which is 15 degrees. So now we know the angle between the vectors is 15.6 degrees. In this case, they're in the same plane, but they don't have to be. A and B can be wherever in three-dimensional direction, and the angle between them will still be the angle right between them. There's only one angle between them. Okay. So it gives you a nifty way to calculate an angle between vectors. Otherwise, it's pretty tricky. In 2D, you can do it by hand pretty easily. Let's see what else. To continue this, I just want to say A dot B is 10 times 7. This is AX multiplied by BX plus that gives us 82.0. Now let's say we've got the freeway X, Y, we have A vector is 15I plus 7J plus 4K. So it's in all three dimensions now we're defining it. This X is our I direction. The Y is the J. And the Z is the K. And we have another vector B, which is 5I plus 9J plus 2K. So let's see. So this one, A, I go out 15 here, back, I go up 7, and I come out in the K direction for like this, right? So like this, I go up, and then I come this way. So that's that vector A. This value was 10, in that direction I went up 7, and I came back to get to that. That's A. Get the drop closer. And then the B, I go out 5, right, half the way. I go up 9, just more actually. And then this is 5, 9, and then I come back. And then that must be B, right? This is a 90-degree turn, this is a 90-degree turn, that was 90, okay. So in three-dimensional space, we have two vectors, A and B. It's kind of hard to sketch, but these values indicate. And I have the magnitude of A is 15 squared plus 7 squared plus 4 squared. Square root. And B is 5 squared plus 9 squared plus 2 squared square root. So it's a hypotenuse, but all three dimensions instead of this one number squared plus another is all three squared square roots. Same idea, same correctness. 17.03, and this is 10.4. That. I have AX is 15. AY is 7. AZ is 4. DX is 5. DY is 9. And BC is 2. So cosine of theta is AX dx plus AY by plus AZ BC, not C, divided by 8. So that's 15, AX bx, 15 times 5, plus AY by, 7 times 9, plus 4 times 2, AZ BC. Divided by the magnitude A and B, 17.02, multiplied by 10.4. Cosine of theta is 0.810, 0.8173. Theta is the arc cosine of that. Uh, 35.2 degrees. So the angle in three-dimensional space between the two vectors originating from the same point, this angle here. So this angle isn't in the XY or YZ plane, it's in 3D space, okay? But there's an angle between them that you could just rotate, right, between the lines. So the plane, in the plane that makes up the two vectors A and B, whatever that is, that's 35.2 degrees. Which is pretty cool that you can calculate that. A dot B is AX dx plus AY by plus AZ bc. So this is 15 times 5 plus 7 times 9 plus 4 times 2. Equals 146. And say check. check on our angle, make sure it's right. So AB cosine theta is 17.13 times 10.49 times the cosine of that angle we calculated, which was 35.2 degrees. And from this, we also get 146. So it agrees with the dot product.